Monday. No, we got more head nods. I'll take it. I saw two pictures I thought were interesting that we could discuss that all of you have probably observed and maybe not thought about or realized. Here's one of them. When the sun sets and it goes through the atmosphere, we talked about it scattering the higher frequencies of violet and blue, and thus the red's getting through. We also mentioned how it can refract, thus like on a total lunar eclipse, it'll still look red, because even though the moon's completely in the Earth's shadow, it's still getting light bathed on it, and it's because the light is refracted through our atmosphere. Well, that same thing happens on sunrises and sunsets. So when the sun is actually down here, compared to us over here on the Earth, it's going through a lot of atmosphere, and the green dashed lines are straight lines. If the light came straight at us, it'd be like this. But instead, let's say a light ray that heads up in this direction, when it enters the atmosphere, it changes speeds. It gets delayed. And so it refracts like our mirage did, and it bends into our eyeball instead of landing above us where we wouldn't have seen that ray. And so where do we think it came from? Well, it's entering our eye from this direction, so we see the sun right here. We don't think anything of it because it's just like, look, the sun's over there. But when it's low on the horizon, sunrise or sunset, where we see it, it's actually already a little lower in reality. That's kind of cool. There's another illusion for you. So before we see the sun actually set, it's already set. It's below our line of sight. It's just the light that's coming up that normally would have gone over our head gets bent into our eyeball. We still see it. I thought that was cool. There's a similar idea with fish when you're looking at something underwater. How many of you have ever gone swimming and you see a quarter on the bottom or a penny, and you go to reach for it just to find out you miss? You always, oh, whoop. You usually have to go a little lower. That's refraction also. Or say you're spear fishing, where you're trying to throw a spear to catch a fish versus hitting it with a laser gun. You see the fish right here. Now this fish emits light rays. They reflect off of it, I should say. And let's look at the ones going this direction. When they change mediums, they bend. Instead of heading up here, they go this way. So we see the fish up here. That's where it looks like it is to us. But it's actually a little lower. So remember that next time, if any of you get on Survivor or something and you got to catch your own fish, it's probably a little lower than you actually think. So if you keep missing, there you go. Any questions on these? All right. I have some clicker questions for you then. Let's see. PowerPoint. We'll use these to review some things. You can see how well you're doing. Start with what I hope's an easy one, but that's why I'm asking it. Because, we talk, there's lots of colors, there's lots of wavelengths. It can bend this way, it can go that way, it can speed up, it can slow down, and it can absorb, reflect, emit, transmit. It can get confusing, so that's why I chose this one. And since it's the first one, and I stall longer on the first ones if you haven't figured out. Today we finish up chapter 29. Warning, this is one of the homeworks that isn't normal. You've had access to it now, but it will be due Wednesday night. Because we're going to have our exam Friday. We'll review next lecture, the exam's Friday, so that you can have time to see the answer key in my explanations. This next homework on just chapter 29, and if you haven't looked already, it's a lot shorter, is due Wednesday. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Well, darn large majority think it's B. Smart whippersnappers, you. Yeah. If something looks red, then that means red is entering our eyeball. How did it get there? It must have bounced off of the thing. It reflected. Good. If it got absorbed, we wouldn't see that light. If it transmitted, it's going the other way, we wouldn't have seen it. Now, something can emit red light. That's true. But that would have to be a light source. Most things don't emit their own light. Pretty much everything you see in this room does not emit its own light except for the light bulbs. Actually, that's not either. It's in the bulb in there. So, questions? All right. Good. I'm glad that one at least wasn't confusing. All right, let's test some color mixing stuff. If you got some magenta and some yellow dots and you put them on a page, they're inks now, pigments. What will you notice? What color will you see from that combination? Sometimes this can be confusing. They're really small, so they're all mixed together, so we see it macroscopically. Or if it helps you, you can think of a magenta and a yellow overlapping. So you got magenta and yellow ink on a page. What will we see? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. Most of you A, red. Correct. Talk me through this one. How do you get red? Glenn. Okay, so magenta is red and blue. Yellow is red and green. It is subtraction. Good. If something is magenta, what color is being subtracted out of the white light? Green. Magenta is red and blue mixed together, so it must be subtracting the green out. Yellow was, you said, red and green, so what's it subtracting out? Blue. It's getting absorbed by the pigment. What's the only one that didn't get absorbed or subtracted out? Red. Red is emitted in magenta and red is in yellow. So yes, we would see red. Questions? So again with this, I like to emphasize what we see is light. And so it's all the addition of colors. Hence, scientists say the primary colors are red, green, and blue, which physiologically is what we respond to. There's a correlation there, yes. So when you're dealing with artists and pigments and whatnot, it's more thinking of how it gets subtracted out or filtered or absorbed, whatever you prefer. So what's the complementary color of blue? Yes, light. It's a complementary color of blue. Because blue, when we see blue, it's blue light. So my shirt. Blue light is reflecting off of it, going into your eyeballs. What would be the complementary color? I admit I haven't used the word complementary much in the lecture, but the book uses it a lot. Where are we at? About 30 of you. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 84% yellow, and isn't it convenient the column's in yellow? Didn't plan that. That's right. That's what complementary means. It's the other two, red and green, which make yellow. So those of you that are artists, that these match on the color wheel. Complementary colors are the ones that are on the opposite side. If you go look at an artist's wheel, it agrees with this. And one more. I chose. All right. The color of light that passes most readily through a thick atmosphere is which of those? In other words, which color makes it through easier? Or goes farther, if you will? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you. Hey, woo. Next was violet. Well, the answer is red. Which wavelengths get scattered the most? Blue and violet. Violet even more. So they don't make it through. That's why our sky looks blue. They just spread all out there. So when we look up at it, it's blue. Think of the sunset. Out in space, the sun's white. It looks yellow to us because some of the violets and blues are already getting scattered as it comes through our atmosphere, leaving what behind? The reds and greens, which make look yellow in our eye. And the more and more atmosphere it goes through, the more and more violet and blue and maybe even some green now are starting to get scattered. And it turns the sun even more red. But red's the one that gets through to our eyeball. Does that help? Any other questions? You can put your clickers away then. Okay. We ended with diffraction. So I'm going to show some diffraction and interference stuff with light now. So I believe it's this one. Let me show you what I have a just an opening. It's a slit. It's a slit of space between this aluminum. We did it with water, where I would make water waves. You could see the crests as the wavefront go, and it passed around an edge or an opening. And what did those waves do? They didn't come out straight anymore. They bent. Diffraction. So refraction is bending because it changes mediums and changes speed, gets slowed down or sped up, delayed or not. Diffraction is still bending of waves, any kind of wave, but it doesn't change mediums. It just gets obstructed by something. So let's obstruct this light with an opening. There it is. So as those waves hit one edge of the slit, they diffract and start bending and spreading out. Well, the other side of the slit does the same thing. And what we have is this thing you've seen before. So just so it maybe remember this? You can think of each of these points as a spot on one edge. And here comes a wave that spreads out. It got bent and now it's diffracting. The other side does the same thing. And if here is the width of the slit, the two edges, you can see that they both diffract, make the waves bend, but then those waves interfere. It's a good review. They can superimpose, and you can get constructive and destructive interference. So with sound, we did this. Here where they line up, they're both in phase because they're both up at that point. This would be a louder sound. And here would be a quieter sound. Loud, quiet. With light, it's bright or dark. bright or dark. We can still destructively or constructively interfere. So that's where these bands come from. That's that pattern. At this dark spot right there, they're out of phase. The two waves that diffracted from the two edges. Does that make sense? If I use a wider slit, here's one my finger can stick through. Let's do it. You can still see diffraction patterns. Or I should say, the result is an interference pattern because they're diffracting from this edge and this edge. It's not as apparent, though. Can you guys see it okay in the back, the difference in light and dark way back there? And here, but it's not as much in the middle. That's because by the time these waves get over there and those over there, light can get through this opening too. Some of the light's not being diffracted as much. And so you don't see the interference pattern here. It's too spread out. You get it from this edge and this edge. And so you see the effect near the edges where it bends. But if you make a smaller opening like we had at first, you can still see that the effect is more apparent near the edges than it is in the middle. But it's a lot smaller, so it still harder to get through without seeing that effect. Lasers are fun. They come out in phase, the light. So there, I send laser light, which just looks like that. All the waves are in phase. That's one of the cool parts about a laser. There's lots of photons and beams coming out, but they're all together. Exactly the same wavelength. We see one color. And I'm going through an opening. It's just really wide, maybe 1/8 of an inch right now. So these waves are too small, the wavelength of red, so it can pass through this opening easily. If I narrow the opening, this gets smaller and smaller, smaller. Oh, there we go. Can you guys start to see that? You can start to see the light and dark pattern. Can you see that in the back by chance? It's small right now. If I go even smaller and smaller and smaller, they spread out even more and more. And this is how I like to think of it. Waves will diffract more the more they interfere with the opening. And so that can happen two ways. The opening can get smaller, and so it's like harder for that same size red wave to get through. And so it's affected more. So things diffract more through smaller openings. Now what if we didn't change the opening, but we just changed the color of light? What if it was purple light? Do you think it would diffract more, less, or the same? Purple has a what size wave compared to red? Bigger or smaller? Well, what do you know about purple that you're confident of? Higher frequency. That part's good. So it's vibrating faster. If we visual back on our slinkies, our spring, it's going faster. It sounds higher. It's a higher pitch. And those waves get closer together too. So the wavelength of violet is shorter. It's smaller. So that it can vibrate faster. So violet is a smaller wave. Now what do you think will happen? Will it diffract more or less than red? Less. Because it can get through easier, the same size opening. So yeah, if you have like a green laser pointer and a red laser pointer, you can go try it. Shine it through some mesh or sometimes clothing. Pantyhose works well. Little openings. It's comparable to the size of the wavelength of the light, and you can see a diffraction pattern, an interference pattern due to diffraction. And yes, if you use your red light, it'll spread out a certain amount. Switch it to green, it won't be spread out as much because the waves are smaller and get through the opening easier. Or just change the opening like I'm doing here. Let's get even smaller. You can spread it out a lot. So one confusion that I had was it looks like there's less diffraction because people see less bright spots. But that's because they're getting spread out even more. They are still over here. but it's harder to see. It gets dimmer. So a smaller opening does make more diffraction. If I make the opening bigger, we'll get less spreading, less diffraction. But wait, I see a lot more spots. Well, that's just because they're all crammed in there where they're brighter. We can do the same thing with two slits. This time, you have two slits that are really close to each other, two openings. So it's like an opening here and an opening there. And so it diffracts from this slit and this slit, and you get an interference pattern. What's neat is, let's make the single slit about the same size, roughly. There we are. Good enough. And so this is the single slit. The center band is wider than the other ones. So here's destructive interference. They're out of phase. Then they're in phase, out of phase, in phase, out of phase, and a phase. Okay, there's a few biologists in here. That's how they had us remember that when in mitosis, when it splits up. They'd make us shout it. But anyway. So you can see the same pattern from here's an edge of a slit or a slit, an edge of the other side or another slit. So you see the same overall pattern due to the two edges. But if you have two slits, they each have an edge. And so they diffract even more. And you get this like sub-pattern of interference because there's two slits. And if you keep adding more and more slits, you can make this more distinct. Those are called diffraction gratings. I'm going to let you guys look through some of those Wednesday. Here's some other fun stuff, though. Here's a wire mesh. No. Let's start with this one. Here's a diffraction grating. Let's turn that one off. And these, it's got like thousands of slits. And they're really close together. How can I tell? Because there's the middle. And there's the first next bright spot. So it's destructively interfering all the way in here. Look how far it spreads them apart. The diffraction is huge. That means it must be going through a really, really small opening. Those slits are really close together.
How come the middle of this case is still small?
Good question. Why does it look smaller? You don't have to know in detail, but the gist is, let's put this one back up to, I think it'll help. That one. So there's the single. And, of course, it's misaligned. Let's get the double back up. There it is. As I added just a second slit, it started subdividing them up into little dots. If I did 3, 4, 5, it starts separating them into dots even more distinctly. And when this diffraction grating that I just had up there has like thousands of slits, and so it just breaks it up. There's more interference, more destructive interference, and yeah, it ended up way over there. I guess this is blocking it. There's one over there too. I don't know if you see it. It's on the window of the door. If I wiggle it a little. Here's a wire mesh. It's not science related. It's just wire mesh. A grid of wires really close together. So it diffracts horizontally and vertically. Like a chicken wire, but really close together. So yeah, it diffracts. There's an opening that way and this way. Here is a fun one somebody made. Diffracts in a cool pattern. And you can design these. You know how much they're going to diffract and where and how they can interfere. They start making these thingies. Here's a holographic procedure they used to make this diffraction grating. So they printed some funky pattern that's unrecognizable if we looked at this under a microscope. But when light goes through it, it diffracts, spreads out, and those waves all interfere in such a way to constructively interfere to show happy faces. That's cool. So when you've seen those glasses where you see snowflakes when you look at lights, the light's coming through the glasses, it diffracts and forms an interference pattern on your eyeball. And so you see bells, snowflakes, Santa Claus, I don't know, whatever they want, snowman. And one of our students was kind enough to donate to science a piece of her hair. Well, that's an edge. That's an obstruction. let's see what happens. I got to go the right way. When light hits it. Getting closer, getting closer, getting closer. Okay, now there it is. So it's missing the hair, and now it hits the hair. Other side of the hair. Back. Sure enough, it's got two edges. Instead of an opening, it's like my arm. This edge diffracts, the waves interfere, and it's just like a single slit. And I'm not going to make you do it, but if you measure this distance to the screen, and how far it is over till it interferes, we know the size of the wave because the laser is a certain wavelength of red. With those three variables, the wavelength and the angle, this distance and this distance gives us the angle, the amount of diffraction. Of course, there's a formula. You can determine how thick the hair is. And it's fun. Yours, in case you care, I'd guess it's about 100 micrometers. That's typical. Most people's hair is about 50 to 100 micrometers. That's a millionth of a meter thick. You couldn't measure that with a meter stick or even a vernier caliper. How do you measure something that small? They use interference and diffraction a lot to measure such small things on the orders of a wavelength of light. We can use light waves to help measure, and that's a really small resolution. So, people with curly hair, the profile of the hair changes. It could be a thick spot, like my arm. If you're looking at it this way, it's thick, but if I turn it this way, it's a little narrower. That's why it curves. So depending on how you rotate your hair, you can change the diffraction pattern. It's like opening and narrowing the slit. That's fun. It even works circularly. I think that's the last one I have here. So here's a really small hole. And I looked right at it. So I will get it centered. There it is. Some of you can start to see it already. So instead of just diffracting off of an edge horizontally or vertically, it does it radially. But it still interferes, and you get these concentric rings. That's cool. And likewise, you can tell how small the hole is by how far these rings are spread out. If you look closely when you do floaters, we talked about floaters, and you see these little circle things, or even your hair or blood vessels. If you see fringes, light and dark fringes going out to the side, or you see rings around something, that's diffraction. The light is diffracting over that small little edge or opening, and they interfere, cast that shadow onto your retina, and you can see the diffraction pattern. Again, interference pattern caused by diffraction. You can actually diagnose how big your cells are that are floating around in your eyeball. Or somebody did this weekend at a teacher conference I was at. If you take a water drop and shine laser through it, it'll act like a lens and project a big swab of light up here. And if you got this like from a pond, the pond scum will float around in there. And when one goes by, it's a really small little spot. The light diffracts around it, and you can see the interference fringes around the pond scum as it goes through past the laser. It's pretty cool. All right. Questions about that? Make pun. Yeah. But you could do it. Mine looks all fancy, but seriously, I've taken like an eyedropper, mounted it, my laser pointer. I usually have to let go of it because I wiggle too much. I just shine it up there, and I end up seeing it. So that's diffraction. So the amount of diffraction is proportional to the wavelength of light. It's easier to get through. It doesn't diffract as much. The opening then matters as well. All right, here's some quantum mechanics things for you to think about. This works for all waves. All. And when you start studying quantum mechanics, matter, all matter, can be represented as a wave. An electron, which we like to think of as this little sphere moving around, actually has what's called a wave function. And you can predict everything we know about it by treating it as a wave. And so you can shoot electrons through an opening, and if the opening's small enough, comparable to the wave of an electron, it diffracts. And you can see an electron diffraction pattern. This works for all matter. You take a baseball and you throw it through a doorway. Whoosh. Technically, it has a wave associated with it. It goes through an opening. It diffracts. And it can be determined how much. If you calculate it, it's about this big. Because the wave of it is so small compared to the huge opening, there's hardly any diffraction that we ever notice. But if we could start throwing this baseball through a very narrow opening at the speed of light, we might be able to see some effects. Heck, when you walk through a door, technically you diffract in quantum mechanics because we can represent yourself as a wave. Weird, huh? So there you go. Next time you walk by some, ooh, did I feel something? No, you won't feel anything, but you can freak your friends out, I guess. All right, let's do some more interference then. This one, how are we doing? Is some bubble solution. Everybody likes bubbles. You see pretty colors. You'll know now why you see colors. I don't know if anybody's thought about it yet. He's nodding, or if you read the book, you've already thought about it. So I got this frame. I'm going to dip it into the bubble solution. Now I have a film of bubble solution hanging there. It's enclosed, so it usually lasts quite a while. I'm going to shine white light on it. See if I can get it onto the screen without blinding anybody over there. Apologize for that. So we can see light is transmitting through, but it's also reflecting off of it. Then I'm going to refract it with this lens. It's a converging lens, and it's going to focus an image onto the screen. Let's dim the lights. Let's try this one. And there it is. Oh, that's gorgeous. Now, this lens flips the image. So this is actually the top of the bubble solution here. Because think of it, the top, so you can see my hand, the top came to into the lens, which then brought the rays together to a focal point. They crossed over and formed the image on here, and so it's upside down. And so you can see gravity pulling stuff down. But you see the fringes? We get color. So these waves, these different wavelengths of color must be interfering somehow. And you guys can tell me. All right, what color is this mostly? Okay, we'll make it easier. How about this one? Green. All right, that means green light made it to the screen here. What colors didn't then? Red and blue. Where'd they go? That's what you should be thinking of. They got filtered out somehow. Was it through absorption? This is transparent. So in this case, it didn't get absorbed by some dye or color or ink or anything. They interfered destructively and to make it here. Now I'll show a picture of how that worked in a second. This one is magenta. That's red and blue. So the green must be filtered out somehow, and it's destructively interfering. We're starting to see a yellow come in here. That's red and green. So blue is starting to be filtered out there. This will change with time. We'll come back to it. Why? Because gravity pulls it all this way, and so it kind of bunches up down here. You can see the fringes are closer together, and here they're farther apart. So I'll let that run a while. It usually takes a while before it pops. And we'll check it out in a moment. Let's talk about why it does that. Let's do this one. Instead of me trying to draw it and messing it up like I've done in the past, I got a picture. Here, this one. So, a similar thing happens. If you have air, and then you go into the, like a layer of gasoline on top of water, you can think of this as the bubble solution, and air again on the other side for what we just saw. The principle is the same here. So here's the incident ray of light, oscillating with a certain wavelength. Some of it reflects. Some of it refracts, comes into here. Some of it refracts again. We're looking at the reflection here off the backside. So it reflects and comes back out as the black one to our eye or to the screen. Well, let's look at this wave that's colored in blue here. Comes in phase. Do you see how they're in phase? It would be if these are the same color of light. Let's say it's blue. They come in here. Well, some of the light that does reflect off the top, like this one, let's focus on that. This light reflects and comes out. But notice, this wave has traveled a little further than this wave. Do you see that? And if it travels an exact multiple, actually a half integer, if it goes a half a wavelength or some multiple of a half wavelength further than the one that bounces off the top, by the time they get back together, they're out of phase. One's up while the other's down. And it's all based on this distance, the thickness, in this case of the gasoline, or in that case the bubble solution. So if that thickness is half a wavelength or some multiple thereof of blue wavelengths, they destructively interfere. You would not see that light here, that color. So if you got rid of blue because it was destructively interfered, you will still see red and green. That's where you'd see a yellow spot. Okay, tell me if I lost anybody. So this is called thin film interference. We see different colors, so we know some colors, wavelengths, frequencies, are getting filtered out. Since it's transparent, in this case, they're getting filtered out by being destructively interfered. So the thickness of our material here, some of it bounces off the front, some of it goes through and bounces off the back. The one that goes through the back had to travel a little further, and if that distance is comparable to the wavelength of a certain color where they get out of phase, that one is destructively interfered and canceled and doesn't reach our eye or the screen. So in this case, I was using blue. It comes in. You got two wavelengths of blue. They're in phase. We see it. One goes through an extra distance, gets out of sync. See how one's up while the other's down? And it goes bye-bye. Yeah?
So the light isn't technically getting absorbed. It's just coming in and out of phase. So it looks like you don't see that color.
Exactly. It's not getting absorbed in this point, in this instance. It's being destructively interfered. Kind of like with the sound. We didn't get rid of sound when you guys heard loud and dead spots. But it was based on where your ear was. The distance you were away from. Remember my two speakers? This one traveled to your a certain distance, so the waves go. Whoosh, whoosh, whoosh. This one does the exact same thing, exact same frequency, exact same wave. Whoosh, whoosh, whoosh. But this one had to travel a little further than this one. And if that distance, they match up so where one's up while the other's down, that sound is canceled, or that light is canceled.
If it gets out of phase, it'll look weird, I guess. It's out of phase in sound.
Yeah, out of phase in sound, it gets quieter. If it's completely out of phase, complete destructive interference, you don't hear anything. With light, we've been seeing it. It's a wave, so it can interfere too. Usually what causes the interference is we did diffracting, so that the waves can start superimposing. Here the waves can superimpose just because the ones reflecting off the front surface line up with the ones reflected off the back surface. So they're superimposed here. And yeah, if they destructively interfere completely, that blue is gone, if that was blue. Or it could be partially dimmed. That's right.
The first one is reflecting earlier, and the black wave is reflecting later, which is why they're out of phase.
It's this extra distance here. This wave, the black wave coming in, reflects here. So they displace these so it's easier to see. You could put this blue wave, this wave, right on top of this one. Let's call it the same wave even. Some of that light will reflect, some of it will refract, and then reflect. Both of these, if the angle is small enough between them, will get into your eyeball and interfere on the screen there. Let me do some interference another way. This might help. We looked at wave crests before. Let's look at the actual waves now. Let's like this one. So again, you can think of these as two edges of a slit, two slits, two speakers, two bobbers in water going up and down, whatever. You got two waves coming out. They're the same frequency. They get over here. See how they're in phase? If they overlap at this spot right here, say that's the screen or your eyeball, see how they're in phase? So that would be loud or bright. Well, let's move over here. If we were over here, see how they're out of phase? That's because this one has had to travel a half a wavelength further than this one. And so it gets them out of phase at that point. Here, they're kind of partially, all in phase, partial, out of phase again. And so this was that light spot, dark spot, light spot, dark spot, light spot. And we saw that on the screen. And you're seeing that now with colors. We're using white light on the soap, but that has a bunch of different wavelengths in it. So when, say, blue is a half wavelength off and it destructively interferes, red and green, because they have different size waves, don't completely cancel. And so we still see those. Let's look at it again. See if things, how they've settled, evolved. So less turbulence because gravity's kind of done its thing. You can see these have spread out more because it's settled to the bottom. And it's easier to see distincter colors. In other words, I can see yellow in here. I can see orange, pink, magenta. I can see green and blue and cyan, and here's a deeper blue. So each in those spots, you can tell how thick the bubble is, the film of bubble. Because I know that right here at yellow, red and green are not being destroyed, canceled out, but blue is. So I know the thickness of that bubble must be some half wavelength or multiple of the wavelength of blue. And it's again here, it repeats. So here it's getting thinner and thinner, and down here thicker and thicker. Other questions? Likewise, for that, you can tell how thick the gasoline is. You can tell, when next time you see colors in a bubble, a round bubble, the same thing's happening. And a lot of things in nature create colors this way. Most of what you see is pigments and dyes absorbing things. If it's at resonance, it absorbs it, and that color goes away. But it can also destructively interfere and go away that way. That works on peacock feathers, for example. It's the spacing of ridges in the feathers, these openings. It's kind of like a thin film. Here's a part of gasoline this thick, or some bubble solution this thick. Or how about a spacing in their feathers that thick? Again, the exact same thing happens. One will go further than the other, and that color could get canceled. Yeah? No, at physical dimension, it's this wide. In other words, my finger is this thick. My hand is this thick. So as that thickness changes, the color that gets destructively interfered can change. Viscosity is the friction of how it flows more, how fast. Butterfly wings. Many of them, if you see a blue morpho butterfly, beautiful. Anybody know what I'm talking about? Oh, okay, thanks. That's interference. Some shells, even the shell of some beetles. You know when you see iridescence? That's most likely from interference. Not pigments doing absorption, but some waves interfering and constructively and destructively interfering. See, these kind of, they're generally the complementary colors that you see more. Cyan, magenta, and yellow. Because it's canceling one of them, red, green, or blue, and the other two mix to make the complementary color. Now to end with, we have the only type of thing I'm covering that doesn't work for all types of waves, and that's polarization. Polarization only works for transverse waves. Light is a transverse wave. Do you remember the difference? Sound was a longitudinal wave. The reason it works for only transverse is because this is what's happening. The light that's coming from the overhead lights, I'm going to show it in the dark here in a moment, but I guess meanwhile, all on. Those electric fields that are vibrating, you can think of it like this. The wave, it's going like this, the electric field. And so in space, and it increases and then decreases, and then increases in the other direction and then decreases like this. So if it's coming at you, you see this. It's in this plane. That would be a polarized wave. Most light is unpolarized. In other words, that electric field, you got a wave that's vibrating in this plane coming at you, but you could also have an electric field vibrating this way, and in all the planes. So this just represents that it's unpolarized. If you send it through a Polaroid film, which these are, or your sunglasses, if they're polarized, this is what happens. Which one gets through? Only the horizontal ones. And so now that it's past it, it was unpolarized over here, the Polaroid just polarized the light. And now it only vibrates in one plane. So if you take a second Polaroid that's horizontal, it can make it through, and you see the light. But if you turn this Polaroid vertical, can't get through. You block the light. That's why polarization only works with transverse waves, hence light. So let's show you that. Here's some unpolarized light. Oh, we can do this with the lights on. Here's a Polaroid. This one will make it polarized vertically. See how it gets a little dimmer? That's because we blocked about half the light, roughly. Now let's take a second one. And if it's aligned the same direction, up, light gets through. But if I rotate it so it's horizontal, it's blocked. So vertical, horizontal. That's what your sunglasses do. When light reflects off of something shiny, like I see a reflection off of this table from the overhead lights, light actually gets partially polarized when it reflects off of non-metallic surfaces. And so the light coming into my eyes is polarized this way, because that's the direction of the surface. It's coming in horizontal. So now you know which way your Polaroid and your Polaroid glasses are aligned. Which way does it need to be? Up, vertical? Let's make it more obvious. Are your sunglasses like this or like this to block that reflected light? Vertical. This light's polarized horizontal, so when you're wearing your glasses, oh yeah, they're like this. It's easy enough. Just take your glasses off and go like this. Whoop, I can see it, now I can't. I can see it, now I can't. I can see it, now I can't. I can see. That's the easiest test to see if somebody's trying to sell you polarized sunglasses that aren't. Wait a minute, you're jipping me here. But that's what your polarized glasses do. Questions? Okay, see you Wednesday. Bring your review questions. Look over the homework and things that are still troubling you or you had difficulty with. We can focus on those.